everyone, I'm Srija Malayala. I'm a software developer at AMD. I have Vaishnavi with me today.
Hi everyone, this is Vaishnavi working at AMD as a software developer.
We are here to talk about the advantages of computational storage devices, the storage applications, more specifically, the file system acceleration and computational storage devices for efficient data storage. As the agenda goes, we are going to first give an overview of computational storage and a quick overview of SmartSSD as we have used that computational storage drive. And then we are going to talk about ZFS and why we picked up ZFS and which compression we have chosen to offload and why. Later, we'll discuss offload design and flow and how much and in what all aspects we have benefited from this. Let's get started. I'm sure everyone here knows what computation storage is, but let's quickly see an overview of its architecture. In the traditional system architecture, memory, CPU, and storage all have very defined purposes. However, with the increased system complexity and with the large amounts of data to be processed in the system, the current architecture shown to the left is showing some bottlenecks. These bottlenecks result from higher CPU utilization for infrastructure tasks or from having to move large amount of data across various components in the system. One solution to solve this problem is to move some of the computations closer to where the data resides. And that is the basic idea behind the computational storage architecture. SNIA defined computational storage as the one that provides computational storage functions coupled to storage, offloading host processing, or reducing data movement. There are three different types of computational storage devices as shown here. The one to the left is a traditional storage device where there is no computation involved. The next one is a computational storage processor where the FPGA drive fits in the SSD drive in the standard slots and communicates with other SSDs over PCIe. The one shown to the right is a computational storage array where the FPGA acts as an accelerator inline in between CPU and SSD. The one shown in between is the computational storage drive where the accelerator is embedded within the SSD. Acceleration scales with the number of SSDs here. We have used SmartSSD for the accelerator and storage. SmartSSD is a computational storage drive in a U.2 form factor with NVMe interface for storage access and FPGA as accelerator. I'm sure you all know what FPGAs are. For those who don't know, FPGAs are configurable architecture that can be optimized for any workload in milliseconds by simply uploading a bit stream. You all must have seen the advantages of FPGA for over a decade now, but the value of the FPGAs is even more pronounced with the computation storage. We see that the technology keeps changing. For example, today we have LZ4 GZIP compressions, and tomorrow there might be a new compression algorithm. With FPGAs, you can always reconfigure and have a new hardware in no time. The storage is accessed using the standard NVMe interface, and the compute engines are accessed using OpenCL interface. Coming to the data flow, usually the data is read from the storage systems to the x86 RAM and then moved to the FPGA DDR for computation. And the result is copied back from the FPGA DDR back to the x86 RAM. In the case of the huge data movement through x86, it affects the overall system performance and the efficiency. Now let's look at how an application running on a host CPU can make use of the SmartSSD to offload compute tasks. The first thing the application does is to trigger DMA to move the input buffer into FPGA DDR. It then triggers the compute engines in the FPGA. The compute engines process the input data and produce results in the output buffer2 as shown here, located in the FPGA DDR. Finally, the application triggers NVMe interface to move the result buffer into the storage. This is the peer-to-peer data transfer, avoiding the host RAM. This is possible because of the 3-port PCIe switch implemented inside the FPGA with its ports connected to host CPU, NVMe SSD, and the FPGA. The entire FPGA DDR is exposed to the host via PCIe bar, allowing the host applications to allocate data buffers from this memory and initiate data transfers directly to or from the SSD using standard NVMe driver stack. So we have offloaded compression from ZFS. Let's see an overview of ZFS and why we chose ZFS in particular. ZFS is an advanced next generation file system built with scalability, reliability, and performance in mind from the ground up. It also has many interesting features like pool storage, where multiple physical disks are combined into bigger storage pools, compression of data blocks before being returned to the physical disks, snapshotting for recoveries from crashes, data integrity using checksum for every block, redundancy and protection with mirroring or RAID-Z configurations. Here are the two different ZFS pool configurations. The one on the top is a mirrored pool configuration, and the one at the bottom is a RAID Z2 configuration. The disk VDEVs at the bottom are the physical VDEVs, and the ones above are the virtual ones. Compression is always triggered at the top level VDEVs. So the compression can be offloaded mainly at three levels: the application level, block level, and the file system level. When offloaded at the application level, we can achieve maximum efficacy because the buffer size to be compressed can be controlled. But the con here is that we'll have to modify every application for offloading. Compression at the block layer in the Linux stack can provide transparent compression without having the applications to modify. But the block size, which is typically 4 KB at the block layer, renders the compression to be less than desirable. The other issue is the overhead of triggering hardware offload for smaller blocks, which can bring down the overall CPU efficiency. The option of doing compression at the file system level can provide an opportunity to achieve the balance between buffer size and offload overhead. The file system level compression also provides transparent compression to applications to achieve the desired cost savings. The larger buffer size also results in higher compression ratios. We therefore chose ZFS to offload compression. Vaishnavi will now walk us through the offload design and flow.
Let us look at the ZFS write pipeline, which is triggered when the application writes data to the ZFS volume. As seen here, the data block is first compressed, optionally encrypted, and a checksum is calculated on it. Later in the pipeline, a disk write is triggered to write the data to the physical disk. I say disks here because the data block may be replicated in case of mirrored pools, or it is striped along with the parity data in case of RAID configurations. And here we have offloaded the compression to FPGA. Now, ZFS compression is supported with different compression algorithms, which user can choose at the time of pool creation. We have LZ4 and GZIP from level 1 to level 9. We have analyzed LZ4 and GZIP level 1 in terms of their compression ratios, throughput, and CPU resource utilization. As you can see here, LZ4 is efficient in terms of higher throughput and lower CPU utilization, but has a lower compression ratio. Whereas GZIP algorithm gives a better compression ratio, but consumes a lot of CPU resources and the throughput is also less. Every application today would want a lossless compression with a better compression ratio. Even though GZIP compared to LZ4 is giving us that, but it's coming at the expense of higher CPU resource utilization and a lower throughput. We can say that an ideal compression algorithm would be one where we can achieve good compression ratio with higher throughput and lesser CPU resource utilization. So we chose GZIP algorithm for offloading. Now let's go back to the write pipeline and see how SmartSSD can be used to offload some of its stages. As seen here, we offload the compression and checksum calculation to FPGA kernels on the SmartSSD. Also, the compressed data is stored on the FPGA DDR, and this buffer is moved to NVMe storage directly during disk write stage of the pipeline. Now let's see an in-depth flow of how the compressed requests from ZFS are handled. The requests from ZFS are transferred to XSS. XSS is an intermediate kernel space library that provides higher level storage acceleration APIs to applications like ZFS. XSS in turn uses XRT APIs. XRT is a runtime library which provides APIs to discover the accelerator devices like smart SSDs, load FPGA kernels, allocate memory in FPGA, execute compute kernels, and transfer data to or from FPGA DDR. First, a buffer object is created by XSS corresponding to the input data. This buffer is allocated in the FPGA DDR and mapped to the host buffer in ZFS. The input data is then transferred from the host memory to the FPGA DDR using a DMA. XSS allocates another buffer for the compressed data. This buffer only exists in the FPGA DDR because in the P2P flow, the data need not be moved back to the host. XSS then creates a command packet that specifies the addresses of input and output buffers and triggers the HLS GZIP compression kernel and then waits for the completion. Once the kernel finishes the operation, the compressed data is available in the output buffer. In the ZIO pipeline, after the compression, the compressed data is further processed for checksum calculation. In case of P2P flow, as the compressed data is in FPGA DDR, it is not ideal to compute checksum on compressed data by the host. Therefore, the default Fletcher-4 checksum algorithm used by ZFS is also offloaded to the FPGA. The checksum computation is done right after the GZIP compression. And then XSS reads the compressed size and 256-bit checksum information from FPGA DDR and passes it to ZFS layer. Another factor which had to be considered while enabling P2P flow is the adaptive replacement cache in ZFS. ZFS by default has the cache enabled. So to support the default settings of ZFS, the compressed data in the FPGA DDR is moved to the cache by performing a DMA using XRT API. Note that this transfer of compressed data to the host is only to update the ARC, which is required for the read operations to find the recently used data in the cache. Finally, at the stage of writing the compressed data to the disk in the ZIO pipeline, the compressed data is moved to the SSD directly from the FPGA DDR. The GZIP compression algorithm used in this work is developed in high-level synthesis language using the Vitis software development platform. The design used to offload data compression to hardware in ZFS is multi-core GZIP compressed streaming kernel attached to a data mover kernel as shown in figure. The data mover kernel reads the source buffer from FPGA DDR and writes to the input stream of GZIP compressed kernel. Similarly, the data mover kernel reads the compressed data from the output stream of GZIP compressed kernel and writes to the P2P destination buffer present in FPGA DDR. There are 8 parallel engines of LZ77, Huffman encoder, etc. inside the GZIP compression kernel, which run simultaneously to improve performance. These kernels are designed in such a way that they can handle multiple compressed requests at once in pipeline fashion using a chaining interface. The kernels are also optimized at every layer internally, which makes them an ideal choice for this architecture. The overall resource utilization numbers for this design on SmartSSD platform are shown to the right. So now Srija will continue to explain about the test setup and the results we have achieved.
We have evaluated the value proposition of ZFS acceleration on SmartSSD using the test configuration shown here. We have created mirror pools, the common configuration used in ZFS. A mirror pool replicates the data returned to one disk to other disks, thus providing the redundancy in case of failures. For example, if you write a chunk of data to the pool, the data is returned to both the disks shown here, so that in case the data is lost from one of the disks for whatever reason, we will always have the data stored in another disk. We have shown 2 disks per volume here, but we can have multiple disks to have more protection. In our test setup, we use Dell 7525 AMD server, which is a dual socket with 64 CPUs. We have used Ubuntu 16.04 and a 4.15 Linux kernel. And for the underlying storage and acceleration, we have used SmartSSDs. After creating the pools and volumes, ZFS gives an option of setting record size and selecting compression algorithm. We have used a default 128 KB block size or the record size as ZFS calls it, and a level 1 GZIP compression. We have used industry standard FIO tool to write data to the pool. We have created 12 threads with an IO size of 10 gig per thread. FIO block size used was 4K with an IO depth of 32. We have also set the buffer compress percentage to 75 so that FIO can generate data which can be compressible. We have created multiple such test configurations, increasing the pools and smart SSDs. We have 4 SSDs with 2 mirror pools, 8 smart SSDs with 4 mirror pools, 12 smart SSDs with 6 mirror pools, and 16 smart SSDs with 8 mirror pools. The FIO is run on all the pools simultaneously here to push the CPU utilization to its maximum. Now let's see how much of an advantage are we talking about with this offloading. We have compared the value proposition against three parameters here: throughput, CPU resource utilization, and system memory efficiency. Let's see the throughput improvement first. We have used FIO tool itself to record IOPS. In case of the multiple pools, we ran FIO on all the pools simultaneously and recorded IOPS from each FIO run and plotted the combined IOPS. On the x-axis, you can see that we are plotted against the number of smart SSDs. So the two smart SSDs here refers to one mirror pool and 4 refers to two mirror pools and so on. We have done this for three scenarios. The one where there is no compression involved, which is the off case, the gray plot here, and the one where the compression is on and the CPU resources are used for compression tasks, the red plot here, and the case where we have offloaded compression tasks to FPGA, which is the smart SSD case, the blue plot. Note that the algorithm used here in both the cases is GZIP level 1. We can see that the offloaded GZIP can give as much as 2x improvement in the performance with higher number of pools. And it's fair to say from the graph that the offloading is as good as no compression in case of throughput. As you can see, there is not much difference in the compression ratios despite the 2x improvement. The next is the CPU resource utilization. The aim was to minimize it so that the resources can be utilized elsewhere. Again, we have plotted this for all the cases from 1 mirror pool to 8 mirror pools using 16 XSDs in total. While FIO is being run, we used Linux MP-stat to record CPU utilization. We have done the same for three scenarios again. We can see that almost 90% of the CPU resources are being used with more pools. We can observe close to 55% decrease in the CPU utilization in case of offload. It's even lesser than the case where the compression is off. That's because we also offloaded checksum, whereas in the compression off case, the CPU resources are being used for the checksum computation. You can see that the value proposition is more visible as the number of pools increase. Along with the improvements in throughput and CPU resource utilization, we have seen improvement in the system memory efficiency. The improvement is due to peer-to-peer data transfer. The memory bandwidth increases as the IOPS increases, and as you can see in the plot, the ratio in case of the compression offload is at the lowest while achieving the same level of IOPS as that of the compression off case, as we saw in the throughput slide. This means that in case of the compression offload, the host memory bandwidth is significantly lesser than that of the compression on CPU bandwidth, thus freeing up the host resources for other application usage. There are a host of other things that can be added to this in the future. I've listed some of them here, like offloading decompression for the read path, GZIP kernel that supports multiple levels, or adding offload to RAID or deduplication features of ZFS. With this, I end my presentation, and please reach us with the questions that you may have through chat box or through our LinkedIn profiles mentioned here. Thank you for taking time to go through our presentation. Please give us your feedback.
Thank you.